Okay, welcome to the lecture 3 and session 2. We are going to start here. And in the previous session, we have seen that how a problem solving agent works. Okay, so we don't have any questions. We are on that. So let's do it by yourself. Let's assume that this particular map is given to you, and this is here is the Arad, and where is the Bucharest? Where is the Bucharest? Here is the Bucharest. So you want to reach at this particular location. Alright, 3 roads are there, Jerind and Cebu and Timisoara. So these are the 2 roads, and when all the things are given, you can see that you can go by this road, then you can come in this road. I think you are going to spend more than 140. Therefore, you would not go to Zerind, and then only thing is where you should go by Timiros or Cebu. Then you can see that 140 is there, 118 is there. So you can take this decision. But that would be a wrong decision. If you comprehensively compute all the distances, then you can see that, because at the first moment you can take this small thing, but after that you have to travel a lot. But here in this 140, the first distance is 140, then 80 and I think 80 and 97 and 101, and very easily you can reach. So okay, so you understood that solving this problem this is the one way that we have in this example. We have seen that even if you only go for the solutions that are going to give you benefit into the right current situation, then it would not be a good idea. You have to see the comprehensive thing, and then you have to take the decision. Let us go back to this toy model, that is a vacuum cleaner. So this vacuum cleaner had how many states? 2 rooms. Okay, A and B, 2 rooms we had, and there could be a dirt, and the vacuum cleaner can take the decision that left and right it can move and suck. 3 operations you can perform. Okay. So can anybody tell me that what is the state space of this particular problem? Means how many different states are there? How many different states are there in this problem? Okay. So let me just take this and let me put it here so that okay, let me just put it that how many states we have. Okay, how many different states we have. Okay, and how many states we can define? 3 states. Okay, right. Somebody is telling 3 states we can define. Let me just see that. I think that a state can be defined using this, that you have a room A. Let me just take a pen. You can define that the room A is there and room B is there. So you see that this is the state where both the rooms are clean. Okay. Second thing could be that 2 rooms you have and there is some dirt, and the third state could be that 2 rooms there is some dirt, and the fourth state could be that dirt is at both the places. Okay, and in all the cases, what can happen that you had okay, right. Let me just quickly step down. Okay, in all the cases, what you can take, that two situations could be there. That when this was the scenario, here was your machine. How to let me just triangle by triangle. Here is the machine. Okay, or it could be possible that the machine is here. This is the state, and the machine is here. Okay, here what can happen? You know that this is the scenario where there is a dirt. This is the scenario where there is a dirt. Okay, so where is the machine? And this scenario where there is a dirt. This scenario where into the room B there is a dirt. This scenario when both the rooms are dirty. This scenario where both the rooms are dirty. Okay, let me just draw that. Where is my machine? So here was my machine. Here was my machine. Here could be my machine, and here machine is in this state. It is a new state. Okay, and here can be machine. Here can be my machine. Here can be my machine, or here can be machine. So you see how many states are possible. Okay, how many states are possible? Can anybody now tell? Okay, in a state space, how many states are possible? 8 states, correct. Okay, right now, right. All right. So here it is. How many states are possible? Because room could be A and B, and into the second place, no dirt, one dirty room, and two dirty room. In no dirt, one room. Two dirty rooms is also one room, but one dirty room could be of the two types. Overall, four cases is there, 2 to the power 2, and then this is AB multiplied by 8 number of state. So can you define the state space? The complete state space is this. You see this diagram that initially, let's assume that this is the state where you assume that this particular both the square brackets represent a single state. Okay, so you are here and you take the left. What is going to happen? Nothing going to happen because you cannot go left. If you take right, you are going into this state, and this is a new thing. You take the left, you go to this place only. You take the right, nothing is going to happen. You see how nicely the things are connected. Then from the here, if you suck, then what would happen? This here there would be no dirt, and then you are into the next state. Okay. So if you take left, you are not going to be there. If you suck, nothing going to happen. If you take right, you come here. And here if you take left, nothing going to happen. Sorry, right, nothing going to happen. Left, you go there. So similarly, you can see that you can build this thing. So although I have built over here, but I suggest you that once you go and try to by yourself develop all these models. That would be very interesting to see. Okay, that for example, if you're here, if you suck, then this is clear, and then you take right. At every place you have to see that for all the three actions, how do you take these actions and what is going to happen, in which state you are going to reach. You have to develop these things. So you see that in this way you can develop all the state space. And then the problem of search. What is the problem of search? That from here to here, how you can reach. So you can see that, for example, if you want to reach into this state, then how to reach over there. So let's assume that you start by this. So search is then easy because from here to here and then here to here. If you say that any of them is a final state, then from here, let's assume that you are into this state. How to come into this state? You say that you take the left and then you do suck, and then you are into this state. Then take right. You can find out that now the things are easy when you develop the state space, and then the searching becomes possible. I have a question. In the second step, suck is not clear. Okay, so let me tell you once again. First, the question is, in the second step, suck is not clear. Correct? Let me ask you a question, simple question. So can you identify these all 8 states? Can you write yes, that you identify that all these states are different? Okay, you understand this. So this is let's assume that you are into this state. So you take the left, nothing is going to happen. Are you with me? If you take the right, you go into this state. Are you with me? If you take the right, nothing is going to change. You are with me. And if you are here and you apply the suck operation, what is going to happen? There will be no dirt over here. And then this new state comes. You are with me? Is it clear? So have I answered your question? That what is the suck operation? That when you apply suck, the dirt in that particular room gets cleaned. Okay. So is it whether your question has been answered? After second step, where is the second step? Here you want to ask the question that if you take the right, then you go here. Okay, if you take the right, you go here. But here, if you suck, what is going to happen? This particular thing would be here, and there is no dirt over here. So you reach into this state. What is the problem? Is it right? What was it the question? Was it a confusion? Because you take the yes suck, then you go to this state. So that's pretty straightforward. Okay, so that's not difficult. There is a suck loop. So there is a suck loop. Okay, so you want to find out why there is a suck loop. Let it be the loop. That is not a problem, because you are thinking that if there is no dirt, then why it is sucking. And that is not an issue. But if your floor is clean, you can again clean that. But it is not going to have any effect. So if you do a suck, nothing is going to happen. Is it clear? Suck loop would be there because in every state you can perform these operations. So if you are here, cannot you apply the suck? Yes, you can apply. So if you apply the self, what would happen? Nothing would happen. Okay. Okay. So I think I'm going to get a question. Anybody asking a question? Akash, not able to understand the concept of loops. Oh, there is no concept of loop. Just tell me that if you apply this thing, where would you go? If you are into this state, you apply suck. So you are not going to change any state, because can you map to any other state, because all the 8 states are shown over there. You would not go to any other state. You would remain into the same state. It is clear. It's not the loop. It just say that if you apply the suck, then you are into the same state. If you are applying the R, you are into the same state. Okay. Okay. The loop, it is not like that. It is telling that if you apply, then what is the next step? Is still not changing, then why we are applying the loop? Question is, if the state is not changing, then why we are applying the loop? My point is, I am only specifying the state space. Means if you are into this state, if you apply the suck, you will be into this state. I am not telling that you apply this. Okay. I am not telling you that you apply this. You don't apply this. My question is, don't apply this. But my question is, if you are into this state, you are applying this, then it is going to be, you are going to into same state. Therefore, a good search algorithm should not say that in this particular state it should apply suck. Are you able to see this? Okay, I'm repeating your words only, that if you are into this state, you should not apply suck, because suck is not going to change any state. If you are here, you should not apply the right move, because right is not going to change any state. He's asking some question is, sir, third state sucking is correct? What is third state sucking? 1, 2, 3 sucking. You are saying sucking is correct. I'm telling that sucking is not correct. Okay. If we say that my performance, what is my performance measure? My performance measure is this, that how much electricity I am going to consume. If this is the efficiency parameter, then sucking is not correct, because it is continuously sucking, because into this state there is no dirt, so what to clean? If somebody pours some dirt over here, then it immediately goes from here to here, and then he should move, and then he should apply the sucking, and he would come into this place. So similarly, if there is no dirt, applying the suck operation is inefficient. Okay. Somebody is asking why loop is not in the first or second state. Loop, if you apply suck into this state, you cannot be into the same state. You come into this state, because there would be no dirt. So your state could change. Correct? If you are here, you apply suck, your state would be changed, because then there would be no dirt. Okay? I mean third set, sixth state. Third set, 1, 2, 3. Is there any meaning of direction of the arrow of the suck? Achha. Yes, there is a meaning. Okay, but look, first thing, I think you are getting a confusion over here. The confusion is very simple, and that should be dealt into this way. Let me just tell you, and this is what that I tell you this, that I'm going to remove this. I'm going to tell you this thing, and that is very important point, that please, you know that this thing, that there is a device and there is dirt, that is a state 1. You say that there is a dirt and there is a this, and dirt is a state 2. And similarly, you say that there is a machine and there is a dirt, state 3. You say that there is nothing, there is a machine and there is a dirt, is state 4. Okay, you list down all the 8 states, and then you remove this. You say that 1. Okay, big thing, 1. Okay, you write this, nothing is there. Similarly here, 2 is written over there. Similarly here, 3 is written over there. Similarly here, 4 is written there. You understand? So you don't see that what is inside. You just see that these are the states. Can you see now? it's a kind of automata. Okay, you see that if you apply this particular thing, you are going to be into this state. Just for the illustration, somebody has initially I started that saying that these images doesn't mean, these cells doesn't mean here anything. They comprehensive they cumulative represent a state only. Okay, somebody said, sir, I understood. Thank you, sir. Okay, great. So great. So you understand that this thing, both the things means one state. Both the things mean one state. They are different. Only this is the important. Okay. Now from one state to another state transition we have talked about. So let us talk some of the problems. Okay. So we have seen till now we have seen that if we have a problem, how to specify and what are the things that we are going to use, how to specify the state space. Let us see some of the problems and then we have to specify these 5-6 things. Okay, at any state, any of the three, the question, I have a question that at any state, any of the three operation can be applied, right? Yes, and in every state, any of the three operation can be applied, and where we are going to go, we have to tell this. Okay, so now we are going to see some of the problem. Can you see this? I think everybody knows that this is a 8 puzzle thing where some number is there. They look 1, 3, 8, 5, 6, and there is a space. So you can just move this space over here. So what would happen if you move this space over here? 6 would come here. Okay, you must have played this game. It is a kind of game, 8 puzzle game. You slide 5 over here. You can take then there would be a blank space, and then you can slide that down. Then it goes away. So you do these kind of changes, and then ultimately you have to reach into these goal states. Okay, so can you see this? Okay, so can anybody tell that how many states are there? I mean, how many total number of states possible over here? Okay, how many total number of states possible? Okay, can anybody tell in this problem? In how many states you can reach the state space? Somebody is telling 9. Okay, so what could happen that since this is the grid, what may happen? Let me represent 0 by saying that there is nothing, there is a hole. So I have 10 number. How many values I have? 0 to 9. Okay. So here I can put. Okay. Here I can put 10 numbers at this place. Na? How many numbers I can? No, I have only 9 numbers. Okay. 0 to 8. Okay. This is the biggest number is 8. 9 is not there. So how many different numbers? 9. So any of them I can put. I can put 9 numbers over there. But how many numbers I can plate over here? 8, because one number has already been placed, so I don't have any choice. So it is up to you. Let's assume that I write 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and I'm going to 1 by 10 choose. Let's assume that I have chosen 3. I can put 3 over here. So in how many ways I can choose? There were 8, 9 choices that I can take, but I have chosen 3. That is fine. That is up to me. Now if I want to put the second place, how many choices I have? 3 has gone. I don't have the 3. How many numbers I have? 8 numbers. So let's assume that I have chosen 7. I have chosen 7, but I had 8 choices only. Okay. Next number I have to pick. So how many choices I have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 7 choices I have. 7 choices I have. Let's assume that I have put 8 over here. Okay. So similarly, you can see that at this place there are 6 choices, here 5 choices, 4 choices, 3 choices, 2 choices, and there is whatever left I have to put over here. So there are factorial 9 ways I can build this thing. Okay, I can 9 things that I can build over there. So how many states I have? Factorial 9. Everybody with me? How many states we have? Is factorial 9. Okay. And again, but then again, we have a problem that the domain experts tells that all the problems means if you create, let's assume that you create this thing. So can you solve them to reach at this particular place? It may not be possible. So they tell that half of them are such that you cannot reach over there to the solutions. Okay. So therefore, total number of state is factorial 9 by 2. Correct? Which is the initial state? Can anybody tell which is the initial state? initial state is not specified. Any state, if you take any configuration, it's the initial state, and then your task is to tell me that what are the moves required. Okay, what are the actions? Action could be up, down, left, and right. These only the actions are possible, because for this for the whole, you can take only left, right, up, and down. If it is here, you can take only up and right. But actions are possible. You are taking the left, then it is not going to change the state. It is only the case. So how many actions are possible? How many actions are possible? Four actions are possible. Okay, left, right, up, down. Okay. What is the transition model that you define? That you by yourself define. That what is the transition model? Let me just tell you. Okay, the transition model is like this: that you say that. Again, the same concept I want to pick. Let's assume the first state, second state, third state. Okay, so how many states? First state. Let me write the first state be 0, 1, 2, 3, 4, 5, 6, 7, 8. What do we mean by 1, 2, 3, 4, 5, 6, 7, 8? That in this grid, 0 is whole is here. 1, 2, 3, 4, 5, 6, 7, 8. This is by mean, huh? I mean by this. So this is the first state. What is the second? Second could be, let me just write 0, 2, 1, 3, 4, 5, 6, 7, 8. So you can same way you can construct this particular case. What is third? I write anything and I create this event. Okay, I can create this board position. Similarly, how many different of I can create? Factorial 9 by 2 number of states I can create. So let me just write first, second, third. All the states I have written factorial 9 by 2. Okay. Then what action I can take in this one? If I take down in this, let's assume, let me write 5. Fifth state is this. It is if I take it down, what would happen? 3 would be there. 3, 1, 2, then 0. 0 would be here. 0, 4, 5, 6, 7, 8. Okay. So if I take this down, so I can say 3, 4, 5, fixed state. If I take that down, DOWN, then I would reach to this state. Okay. So similarly, if you take from this, if you take up from this, if you would go to this particular place. Okay. So similarly, you can make the diagram. This is what I am asking here. I'm telling that state and what is the transition model. You can say that this is a transition model. What is the goal test? Goal state is this. Here, if you go to this, and then you see the goal state. Pathcast are, you can say that one is for every move there is a cast of 1. There is a question. Let me just take it. Why, sir? Can you please explain why factorial 9 is divided by 2? Okay, I told you that factorial 9 is divided by 2 because you can construct any situation. But my point is that if you create this particular board position, whether you would be able to reach this goal state or not. So people had identified that half of the state, if you construct like this, they cannot reach to the goal state. Because whatever you do, you cannot reach to the goal state. You cannot solve them because if you change some of the things. So therefore, it is divided by 2. So only those can be states because if you go from here to here, then only you can go from here to here. So if you cannot reach the goal state, so those things cannot also be into the initial state. Okay. So you understand this. Okay. So goal test you understand. What is the pathcast? Pathcast I told you. Pathcast is 1. Whenever you are performing one thing, then you are adding 1 to that. You want to solve that very easily. Let's see the different problem. This is the 8 queens problems where you have to put 8 queens under the chessboard so that they are not attacking each other. So I say 4 queens. If you have only 4 queens and you have to put such that they are not attacking, you see that this is not attacking on any of them. Second one is also not attacking on anything. Third is not attacking anyone. Fourth is here, not attacking anyone. Fifth is here, not attacking. Sixth is here, not attacking. Seventh is here. Eighth is here. You see that, okay? No one is attacking. So can you tell me what is the states? How many states are there? So all possible because you can put anywhere, anywhere you can put the 8 queens. So first queen you can put at how many places? 64 places. Okay. How many places you can put the first one? 64 places. Okay, let me go here. Okay, so I want to find out the states. Okay, the how many states are there? In this. Okay, the first since how many have you have 8? 1, 2, 3, 4, 5, 6, 7, 8. The first one in how many places you can put? 64. Any place you can put because there are 64 places you can put the queen. Second one, but you cannot put everywhere. You can put only 63 places. Fourth one is 62 places. Similarly, 61, then 60, then 59, then 58, because then 57 places. You can put any places. So these are the possible states where you can put the queens. But okay, you can put the queen, but those are not the solution. Solution is only few. Oh, sorry, I missed this. Rightly pointed out by one of our students that the first queen can attack the eighth in this corner one. Okay, so there is a problem. We cannot put it here. So therefore, this is not the right solution. You should try to find out the another solution. Okay. Okay, this is a problem statement only. So this is one of the thing that therefore this is not the right solution. I'm not telling that this is a solution. So okay, so you understood that you assess the problem, what the problem is, and you also understood that the state space is very large, and you can take, and therefore what is the initial state can be anything. Your initial state is a initial 0. There is nothing onto the board. Okay, and then what are the actions? What are the actions? Actions could be that and also you can reformulate the problem in such a way that you put the first queen and then put the second queen in such a way so that it is not being attacked by the previous ones. So therefore, if you define like this, then the first one if you put it here, the second you cannot put into this line. So therefore, the number of places where you can put the second one reduces by a large factor, and therefore then your formulation would have the lesser number of states. Okay. Then initial state, no queens on the board. Actions, you can put a queen anywhere. Transition model, from one state to another you can go. What is the transition model? Okay, how can you go? Transition model is this: initially k number of queens, then it becomes k plus 1 number of queens. Okay, this is what the transition model is. But a goal test, whether there are 8 queens and they are not attacking on each other. This is how you test whether we are into the goal state or not. Next problem, very important problem, and this is also a very difficult kind of problem. Just see that how difficult mathematical concept it is. Knuth conjecture. Okay, this says that use only one number 4. I am going to give you only one number 4, and using this number you can formulate. You can find out any other number. So let's assume I want to find out the 5. Okay, and operations that are allowed to you are only factorial, square root, and the floor operation. So you, for example, here it is saying that if you apply the factorial of 4 and then you apply the factorial of whatever you got, and you take under root, and then if you take the floor operation, then you get 5. See how difficult it is, because this number is going to be very big number. Factorial 4 is 4 multiplied by 3 multiplied by 2, and 4 multiplied by 3 multiplied by 2 is, what is the number? Can anybody tell? 24 looks like. Okay, looks like a 24. Okay, and if you apply the factorial of 24, can anybody tell me what is the factorial of 24? You can solve using internet. Can anybody write what is the factorial of 24? 24. I think it is not possible to compute very easily. Oh, no, factorial. Somebody is writing 4.9 is a factorial. No, it's not the factorial. Factorial is if you multiply 24, then 23, and 22, some such as multiplication, then you will be getting the factorial. It is not going to be a small number. It is going to be very big. Okay, somebody written 6.20 into e to the power 23. Just see 23 number of digits, and then you apply square root 1, 2, 3, 4, 5, 6, and you get 5. So Knuth conjecture is this, that if you apply the right number of operation combination into right number of ways, then you would be able to find any number, and no, there is no proof. So what are the states? How many states we have here? Infinite states we have now. We have initial. What is the initial state? Not initial state. Any single number 4, because you have only 4 number. Then how? Then infinite states, because you infinite possibilities you have to create all the different numbers, and then you say that from this number to this number I want to reach, and what are the all operations? Okay. What are the actions? Actions are the you apply factorial, square root, and floor operation on the numbers. And then what is the transition model? What is the transition model? That one transition to another, that is defined by the mathematical operation, because you know that when you have a number and you apply some factorial or a square root, then you for sure know that what is the next number. So therefore you can find out these are transition made, that you say that initially I have the 4, then you apply the square root, then you go for the 2. Okay, you understand this concept? Is it clear? Very easy, very easy. It's not that difficult. Very easy concept it is, huh? Let me just tell you. Let me just draw some of the functions. You would be with me, okay? So I'm telling that initially you take 4. Initially you take 4. Then you apply square root. Then you get 2. Then you apply square root. You get 1.44 dot dot dot. Then you apply lower. Then you get 1. Okay, you got the one number 1, 2 both. Okay, then you apply square. Okay, then I think you can apply square root. Then you are getting again the 1. You can apply this factorial. Okay, let me write like this, factorial. Then again 2 of factorial is 2, and factorial of 1 is also 1. So really you can build lot of numbers and so and so. Okay, so that's clear. So you know the goal test. What is the goal? The goal would be specified, that I want to find out the 5. Okay, so next is there are some other problems also. You can see them and try to find out. Please explain the path cast again. Path cast would be here 1, because when I'm in the previous case, you can say that every operation is going to take the 1 unit of the effort. So you can say that going from 4 to 5 is how many effort? 1, 2, 3, 4, 5, 6, 7, 8. 8 effort is required. So you can say the goal path is 1, and therefore 5. 1, 2, 3, 4, 5, 6, 7, 8. 8 is the cost. Okay, then we want to find out the more things. Let's see more problems. Route finding. This is we have recently seen that most of the time we are seeing that given a map, we want to find out, I want to go from A to B, how to forward is the route. Touring problem means you want to visit all the city. I give you the map and you want to tour all the cities. And then traveling salesman problem, which tells that you only need to want to visit every city once, no city twice. And you have to come back in such a way that is there a possibility that you can visit all the places into the map without repeating any place? So this is the traveling salesman problem. VLSI layout, most of the time you see that the VLSI components need to be packed very tightly, so that less wiring is required and less power is required. That is also a very difficult problem, because the combinatorics make them very high. Okay, robot navigation. You have a robot, you want to take it out and you perform some of the operation. Very complex situations, because a robot in itself can be very complex design, because of the various joints, and it is going to perform some of the operations. It is standing, going up, going down, moving forward, moving backward, doing something. So very high dimensional problem. Automatic assembly sequencing, it is also a difficult problem. Means you want to build something, so you want to tell that these things should be combined, so that at the end this particular product come. The very important part is this: if you change the sequence, it may be possible that at the end you cannot add more items, and therefore you have to redo some things to put something inside. So there should be a proper sequence, so that until there is a proper sequence is there, you cannot assemble all these things. These things are problems. So you try to find out some of those things and try to see that how you can define those parameters. Okay, 5 parameters. So when you define those things, okay, when you define the states and when you define that what is their transactions, what is their how they are related, then a graph comes up, okay. Then you start searching in that. So for example, in our previous example, you start from the array, then you see that you explore that after expand array, you into this state, you expand the array and you try to see Cebu, Tibusova and Zerend, three places, and then you decide that where to go, and you decided that I would go to the Cebu, and then you take the Cebu and then you expand once again. Sometimes it may be possible that here is a big problem that from Cebu you can go ahead, because already you can Cebu, the Cebu you can go ahead, you expand, you again find out this. So you have to take care of this thing. The places where you have already visited, you should not visit, and then you can change the color of this so that at the later point they are in the expandation. When you expand them, they are not appearing once again. So you see that this is the one way that you start from some initial state, you do the expand the operation, and then you find out the right thing and you go ahead and then keep expanding until you find out, until you reach to the goal state. This is a very basic algorithm, and I hope you know this. That is not a big problem, and this only says that if you want to search into the somewhere, what you have to find out, same thing, that a frontier, if the frontier is empty. What is a frontier? Frontier means there is some list now from which you take out some of the things. So initially that link, that particular list contains only the initial state, but when you take out the initial state, you put all the places where from the who are the nearby, because here in this example initially array is there, but when you expanded this, you got Cebu, Tamishini and Zerend over there. You put these things over there. How you are putting that is again a question. Then from Cebu you put all these things which are going to come into the frontier, and one by one frontier is expanded, and you take the first node from the frontier and you execute the algorithm on that. If nothing is into the frontier, then you are failed, because you cannot find out any next path. This is a visualization that is not much important, but say that from initially you find out that these three places need to be explored, then you came here and you saw that these two places need to be explored, and here you find out the second thing, and there you applying some logic. Let's assume, let's not go into the detail of that. You find out that you are expanding into this way. Let's assume that you are expanding into this way. Okay, so one such algorithm is BFS algorithm, breadth first algorithm. I think you know this algorithm. I have brought this from the book of Corman, and I hope you understand this algorithm. And I can explain this algorithm very well, but I hope that I should not. If it is new for you, then I can explain this. Okay. So otherwise, if you know these things, so these things are pretty basic. So let me just only go to the example. Okay, let's assume that you are here into this. Okay, so I'm going to tell you that what are the sequence that when you are going to apply the breadth first search into this particular graph. Okay, let me just tell you this thing. So here we have a graph, and let's assume that we start from the S. This is shown by the Q. That in this Q initially only S is there, and then it sees that what are the places which are nearby. Why it is infinite? Because initially everything is disconnected. It is going to see that what are places nearby. It says that R and W are near. So it puts W and R in any order you can put. W and R put, and it makes S black because S has been visited, and then it takes out, or S is removed for the Q because S has been visited. Then from here it takes out the W. W is removed, and whatever things are nearby the W. What is nearby the W? X and R, T. So T and X, it has been included into this Q. W has been removed, and its color has been made black. Places which are currently inside the queue and they are not being visited, they are made gray. So they are made gray, and you see that this is what we have. Then we take out the R, and then when we take out the R, this R becomes again, R also becomes black. You see the R becomes black, and what is nearby the R? It is V. V is placed behind this. So into the best first search, we implement a queue. That is important thing, and therefore this is what the sequence we have. Okay, so 2 is here. Then we see the next item, that's T. So you see that T becomes black. Nearby items that are X and W, X and M. But since X was already inside the Q, it has not been placed. Now the U has been placed. U has been also placed, and you see that this is the sequence in the items are actually you are discovering. So if you find this was happens to be a goal state, you would stop at this particular moment. Okay, so when you make the things black, you kind of stop over there also. So similarly, the X, this time X is going to be removed. You see that it is black, and here X new item Y has been included into this, and then you see you remove V. You remove V, nothing has been added because all other things are black or gray. It is black. Then you remove U also. Then U is also black. You see. Then Y, and you see that all the things are now black. Another algorithm that is important over here is the depth first search. All these things are called blind search algorithm because you don't have any other information about the environment. You don't have any information about the environment except the how they are connected. So and this connection information you disclose one by one when you go on to them, and then only you disclose. So this is kind of blind search. You are not seeing anything. You are only seeing your first handle, and then by this you are actually one by one going one place to another. So DFS, this is the algorithm, and this first search algorithm where you start from Y. There is a counter that tells that when you enter, at what time you enter into this particular thing, and after finishing when you went out. So initially 1, and then there are 2 places to go. So let's assume that you go here, so you put 2, and from here there are 2 places to go. So let's assume you go into this way, so it is 3. Then let's assume there is 1 place to go, so therefore it is 4, and there is no place to go from here, so therefore 4 by 5. 4 by 5, you are done. Then this you come back from the same path, 4 by 5, 4 by 6, then you come here 4 by 7, and then you come 4 by 8. 4 by 8, everything is done, and when there is no place to go, then the algorithm chooses the one of the node that is free, that has not been each vertex. You do this. If it is white, you do, and since you find out one vertex white, then you start entering over here 9 by something, and this was a new place, then 10 by something, 10 by something, then since there is no place to go, 10 by 11, then 9 by 12. So this is the depth first and best search algorithm. The depth first goes inside, then try to find out the things. These are the 2 algorithms that we have discussed in this class, DFS and BFS. In the next class, we will be seeing some of the algorithms that involves some heuristics, okay, and they would be better algorithms. So that's all for today. Thank you for joining me, and I would be keep taking questions. Please ask the questions if you have. Okay.